This last example comes from your textbook on page 310, number 54. So we'll read it here. NCAA collected data on graduation rates of athletes in Division I in the mid-1980s. Among 2,332 men, they found 1,343 had not graduated from college, and among the 959 women, they found that 441 had not graduated. Use these data to test the null hypothesis that the proportions of graduation rates for men and women are equal. Okay, well, that was my calculator falling off the chair. Why is this a percentage problem? Well, probably the biggest tip-off is that there was no standard deviation given to you. What we calculate is a proportion who graduate or do not graduate for each men and women. And so we'll be calculating proportions or percentages. Now, a little word about proportion and percentages. Proportions in this textbook mean decimal versions, and of course percentages are percentages. So I tend to use all percentages, and I believe my formula probably looks a little different than the textbook because of that. So anyway, I'm going to write the numbers on the board. I often get the question, how do you know we're testing two means here? Do you remember the problem with the Baptists and the Methodists in Detroit? So they had the number of, from a sample of 190 people, they had so many people were Baptists and so many people were Methodists. And on the surface it might look like you're comparing two percentages there, but no, we weren't, because one number depended on the other. In other words, the percentage of Baptists in that problem depended upon the percentage of Methodists in that sample, and vice versa. Now in this case, the one does not depend upon the other. You see, we have 2,332 men that they studied and 959 women, and these percentages, not only are they different, they do not add up to 100%. So they're not complementary of one another. You don't get one percentage from the other percentage. They have to be calculated separately. So that's a tip-off that we have two percentages that we're comparing. And it's a percentage problem, again, because there's no standard deviation given. And but we calculate percentages. Well, that's some clues there. I know that's always a kind of a struggle for many people in this class, looking at the problem and determining what kind of statistics do I use on it. Is it comparing two means, two percentages, one mean, one percentage? You know, what kind of problem is it? Well, so I took the non-graduation rate for men was 57.6%. The non-graduation for women athletes was 46.0%. So let's construct our hypothesis test. The null hypothesis, you see, we're testing to see if there's a difference between men and women in the graduation rates. And the sample sure seems to indicate it, but we're testing it statistically. Remember the last problem, yes, summer classes scored higher than winter class. That summer class scored higher than the winter class, but when we tested the difference, it wasn't a big enough difference to make a statistical conclusion that they were different. Kind of the same issue here. Is this difference significant enough to say that fewer men graduate or more men do not graduate in the athletes than the women? I'm going to guess. Very large samples, this is probably going to be very significant statistically. But we'll see. All right, null hypothesis then would be what? Well, if we're testing to see if one is higher than the other, then the null would be that they're the same. And so the population percentage for men is the same as for women. Now I use the capital Pi for population percentage. So these are representative of the entire population of male and female athletes in the NCAA Division I. That's representative of it from the sample. And so there'll be no, in plain English, no difference. And graduation rates graduation rates. And then the alternative hypothesis is that the non-graduation rate for men is greater than that for women. So mu m greater than, pi m greater than pi w. So this would be more men fail to graduate than the women. Well, that's sort of the structure of our hypothesis test, and I see I goofed a little bit. I wrote H0 here, and this is the alternative hypothesis. That should be HA. H0, HA. The calculation for this type of problem, comparing two population percentages, is found on page 298. Page 298. I'm sorry, 297. Page 297. And because it involves percentages, proportions, those problems we calculate a z-score rather than a t-score. So we're comparing means, you're calculating t-scores according to the student's t-distribution. You're calculating percentages, you're calculating the standard normal distribution, the z-scores. And if you're wondering why there's a difference there, kind of technical, but we're actually doing something I think rather interesting here. The true distribution for this problem would be a binomial distribution. And I don't know if you recall that discussion from chapter 4, I believe. Binomial distribution is a discrete distribution, looks like bar graphs. This is bar graph type data, except the calculated using the binomial distribution calculations would be rather tough on a calculator. A calculator may not be hold enough information to do that. So what we do is, on large samples with percentages, this is kind of behind the scenes stuff, we're using the standard normal distribution, the bell curve, to estimate the binomial distribution. So if you studied a more calculation intensive course, like a traditional statistics course, you would learn when you could do that, when you get by with that. Well, anyway, we can get by with that in this course because keep it a little simpler.